Okay, so welcome for the next BrnoJUG. Today we have Jaro Hamala talking about 1 billion row challenge, which was a really great idea by Gunnar Morling in this January. So hopefully you will learn something. Floor is yours.
Thank you, Martin. Hello, everyone. It's great to see so many faces here. It's perfect. Thanks, Martin, for the invitation. My name is Jaromír. I'm a software developer at QuestDB, which if you happen not to know QuestDB, shame on you. It's the fastest open source database. I mean, for time series. And I'm not a performance specialist. I do not consider myself to be someone who is specialized only in performance, but I like to say that I have a bias for performance. So I'm a generalist who likes to, poke stuff to make it faster. So when Gunnar Morling, do you know who knows Gunnar Morling? Okay, not too many. I thought that this was the popular venue for the Red Hat folks. Gunnar Morling is a former Red Hat developer, the founder of the Division project for change data capture. These days, he's with Decodable, working on Flink as a service effectively. And on the 1st of January, he announced this 1 billion row challenge, which was, I hope you can read this, which sounded really simple. Hey, I give you a file with 1 billion rows, and in each row there will be a name of a city, the station, they call it, semicon, and temperature. Your goal is to write a Java program or a program running on top of JVM, written in pure Java. It will do very simple aggregation. So for each station, for each city, it will calculate its minimum temperature, maximum temperature, average, then write it as a single line in this format. So name of the city equals minimum, average, maximum, sorted by alphabet per station. That's it. Sounds simple, right? And it is simple. It's the most basic aggregation you can imagine. And not only that, not only it's simple, he even provided what could be called a reference implementation. So if you check the reference implementation in Java, this is pretty standard Java, right? It's using the streams, which has been in the platform since Java 8. It creates a file reader with the input file. It creates a string of lines, right? And then, the strings can be in parallel. Then it will group it by the name. So this is the format into file. So it will, from each line, it will extract the name of the city. If you check the extract name, it will basically take everything up until the semicon, excluding that. And then it will collect it by summarizing double collector, which, if you don't know this, it's also built in inside the JDK. And basically for each entry, it gives you its minimum, maximum, sum, count. So pretty much what we need. And the result of this step is a map. The key is the name of the city. The value of the map is the statistic with min-max. And the next step is to create that format alphabetically sorted thing. So again, for each entry in that map, it will again stream it, and it will collect it into another map. The key, it will take the key as it is, because the key is the name of the city, which is exactly what we need. So we don't need to do any transformation at all. So we just take the entry as it is for key. For value, this is the value which is in this map. So here we need to do this formatting, right? So basically string format, minimum, average, maximum. This is all provided by the JDK by this double summary statistics. This is not important. This is basically for merging. We know that our keys are unique at this point, so this is not used at all. And we collect it into a tree map. Do you know why tree map? Why?
Because it can sort it.
Yes, exactly, because tree map is a sorted map, and we don't provide our comparator, so it will use the natural comparator, natural comparing by the keys. So the output of this is we started, which I should have done. Started to talk about this because now it will run for 2 minutes because it's really slow, but the output will be in the desired format. So I will keep this running for a while, for this roughly 2 minutes, and we can move on a bit. We can talk about the rules while it is all running. So according to the rules of the 1 billion row challenge, there can be in this 1 billion row file, there can be up to 10,000 unique station names. That's the rule. So each valid program has to be able to work with up to 10,000 stations, right? That was the official rule, but in fact, the basic or the official testing set, it has just 400 or so rules. So it means if you are optimizing to win, you can optimize for 400 unique cities, but at the same time, you can have, for example, some slow path, which will work if you happen to have this 1,000, because the measurement, you know, how this is being benchmarked is with this official data set with 400. That's what's used for measuring the performance. But then there are other tests which are measuring or testing the correctness. And the one of the correctness tests is that it uses some mumbo jumbo generated random UTF-8 characters as name of the cities. And if your program cannot cope with 10,000 unique stations, you are disqualified. Another rule, the city names are encoded in the text file in UTF-8, and again, your program has to be able to cope with the station name with up until 100 bytes. So not 100 characters, 100 bytes when encoded in UTF-8. It means if it's all ASCII, then one character is 1 byte, but it must be able to work with non-ASCII characters. So that it can be I don't know, in Arabic, which is multi-byte, in UTF-8, again, you have to be able to cope with that. There's a restriction on the temperature range. So it's fixed format. So it is between this minus 99.9 up to plus 99.9. And there is always this decimal point that you can rely on this. And you do not have to do any kind of a validation. You can assume that the format is exactly as specified. It means that you don't need to validate that there is temperature outside of this range, or maybe there is not a digit at all, but there is some, again, mumbo jumbo. You can take for granted that the format, the input file is well formed. One important rule, which I personally believe made this, the reason why this challenge was quite popular, is that the Gunnar, the founder, he said, you are not only allowed to borrow from each other's solution because they were all in open, but he actively encouraged people to do so. If you check the official rules that this address, the QR, not the one before, then he is actively promoting, hey, this is open source, this is, it's not only about winning, but let's learn from each other. So this was, I think, very important. Another rule, it has to run on JDK, so it has to be JVM based. Some people from other communities were kind of disappointed, but there were like branches where people were measuring a Rust-based solution and C# and C and whatnot, but that was not part of the official competition. And yeah, and how it was measured. So your program was executed 5 times in a row, and out of these 5 executions, he would remove the fastest, the slowest. So there are 3 left, and he averaged that. That was your score, and you could submit as many programs as you wanted. So I submitted, I think, I don't know, maybe 6 different versions. each time with some improvements. And this combined with this cross-pollination, I think that is what pushed the boundary quite a lot. And last thing about the official testing box. So at the end, originally, the original testing box was not this 32 core AMD, blah, 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 blah. The original was 8 core AMD, the same microarchitecture Zen 2, but it was only this low cost kind of cloud Hetzner, if you know that. And it was a shared box, shared instance. And the result was that it was kind of jittery, the results. They were not exactly reproducible. So I think after, I don't know, 1 or 2 weeks, the Gunnar decided to rent a bigger box, a dedicated hardware with no noisy neighbor. And all testing was done on that. So the box was 32 cores, but to obey to the original rules, your program when running was restricted to the 8 cores only. Right? So we had the whole hardware, the 32 cores, but the program for measuring purposes was, I don't know how, maybe he used task set or something, I'm not exactly sure, but it was restricted to 8 cores only. And one consideration, if you have 1 billion rows with the city, semicolon, temperature, and you have normal distribution of cities, as it was in the official measuring set, then the size of the file was 14 gigs. Not too bad, right? So important is that this 14 gigs is less than available RAM. It means that your program should not be bounded by I/O. It should not wait for disk, because basically if it is running 5 times in a row and it fits all in RAM, it should be all in this cache. Right? So we should be able to take advantage of this. Let's have a look. Yes, okay. So our reference implementation just finished. You can see the output here. It's the expected format. Yeah, it looks alphabetically sorted. It looks like a minimum, average, maximum could be about right. Even I don't know where. Do you know where is Abha? I never noticed such massive difference between minimum and maximum. But this is 74, so maybe these are made up temperatures, because I don't think 80. Okay, that's made up unless they measure in sauna.
Do we have Brno there?
Pardon?
Do we have Brno there?
I am not sure. No. There are only significant cities such as. So this was pretty slow. Do you have anyone brave enough to shout? Feel free to shout an idea how to make this faster. I can show you the code once again. Yeah. So, but maybe if you are shy, maybe. I'm shy to join here.
Use the with threads, buffer threads, for example, not strings.
Yeah, I use parallel strings here. That means there will be 4 join pool, so it will use as many cores as I have, right?
But I think the buffer threads are quite faster than strings.
Okay. I think I'm not quite sure if I completely understand you, but I think we will do what you are suggesting. And this parallel strings, well, it looks, it's kind of misleading, right? Because this basically means because we're using on the input, we still have this buffer reader, file reader, single thread. So the step which could possibly be parallelized is this grouping, calculating this average, right? Minimum, maximum, but the I/O will be single threaded, right? So that's not great. That's not great. So we need to think about strategy, how to make even the I/O normalized. Okay, we check the results, and that was kind of like that. Tooling. Yeah, I basically through this talk I will be using 2 basic tools. One is a async profile, which is a profiler, open source Apache 2 license profiler specifically for Java. So I'll be using this, and we will be using perf. And if you don't know, async profile is awesome. It provides the most accurate results from all Java-ish profilers, maybe with the exception of Intel V2. Except this one is much easier to use, and I really recommend it if you don't know it. And it's also super easy to use, at least for the basics, because this doesn't work. It's yeah. Okay, so I have a script for starting the program. I have installed the async profiler, and installing is really too glorious because it really means downloading a tarball, unzip it, and that's it. And part of this tarball is this JVM agent. And if you want to use the profile, one of the ways how you can do it is you just start your JVM with agent path. It takes the path to the profiler. I'm interested in the CPU time, and I want the output to be in this HTML file. And I will not run it again because I already prepared this at home. So the output will be open in browser. Yeah. Output will be like this, flame chart. Like graph chart. Never know. Franciszek, you know, you are the graph guy.
I do. Everyone calls it flame graph, but it should be flame chart.
Okay, are you familiar with this format of displaying profiling information? Okay, half, nodding heads, and basically what I can see here is 2 or 3, depends, big blocks. Like for now, I will ignore this yellow part here, and here I have this big part is the I/O. You can see buffer, readers, heads, next, read lines, on I/O, blah blah blah, new I/O at the end of the day, blah blah blah. And here is the actual calculation. You can see where is it spending time. So okay, I/O calculation, and what is this thing? G1 garbage collector. So I can see quite a lot of time is spent on GC. It's not what I want, right? Even that's G1, so it shouldn't have big pauses, but it's still using CPU, right? And I want CPU time to be spent on running my application, not on, I don't want my application to compete with basically GC or CPU. So that's not great. So we need to fix this too. Before we do that, I promise that I will show you a possible strategy, which I think was adopted by almost everyone in the competition, how to make this IO parallel. So if you think about it, the format is very simple. It's almost embarrassingly parallel. There's a question?
Yeah.
Why? Okay, the question is why I've chosen the async profiler. It's basically the one I know, and is one of the few profilers I actually trust most of the time. It's simple to use. I'm using Mac, but everything is running on Linux. It's easy, unlike vTune, it's easy to control it from command line only. It generates these nice flame graphs. So it's just convenience, let's say accuracy. And it doesn't have this, if you are familiar with profiling and benchmarking, there is this phenomena called, I forgot the name, the bias, basically because of safe pointing and how JVM works internally. So many profilers often lie, all profilers lie, but this one, you know, it's basically, it's telling me the truth more often than the others. That's my experience anyway. Anyway, back to the parallel IO. So it's almost embarrassingly parallel, right? I have this one file. So what I can do, let's imagine I have just 2 CPUs for the sake of simplicity. And let's imagine the file looks like this, right? So, okay, I can say, okay, so I can split it in half, and one CPU will aggregate or pre-aggregate or reduce, if you will, the first half of the file. This will be the output. So for each city, here is just Prague and Berlin for no particular reason, and this will be the output. And the second core will do the same, and then I will do another aggregation step. I will aggregate the results from each CPU, and that should be just a few rows, because we said that the official testing set has just 400 stations and 1 billion row. So if I split this into 2 CPU cores, imagine, let's pretend we have 2 CPU cores, then this CPU will have to process 500 million rows, but the output will be only 400 lines. The second CPU will do the same, and then the next aggregation step, post-aggregation, or next layer of aggregation, will work only with 400 rows from each CPU, which is peanuts, and it will be, you know, the cost of this will be totally dwarfed of the cost of this initial aggregation step. So easy peasy. The only complexity, or not the only, but one non-trivial thing is how exactly to make the split, because let's say the file has 14 gigs and I can't just, you know, point my finger exactly in the middle, because I, you know, the split has to be basically at the end of the line. Right? So the simple strategy, I point my finger and then I go byte until I find the end of the line. The next byte, you know, that's the split. So that's easy. Before we go back to code, one more thing. Who is familiar with memory mapping or memory map files? Or who has ever used memory map files? Okay, not too many. So very briefly, it's basically memory mapping is not Java specific at all. It's on POSIX system, which includes Linux. Yeah, I think it's now POSIX, not sure. Anyway, it's a system call where it allows to take a file and map it into your virtual memory, into your address space, and then you can access the content of the file. You can read the file, or you can even mutate the file sometimes, as if it was just a memory content, right? So basically, it reads the file from the file system. You call on Linux. Now we are not in Java. We are on Linux. We do mmap. We pass and handle whatever, and the mmap call will return as a pointer to the basically memory address, and then everything what was in that file is magically in our memory. So what I can do, okay, now we can go to Java. We can go to Java. So the good news is that Java has a support and has had since, I think, new IO, which is Java 1.4, ancient history really. So in Java JDK, since the new IO was introduced, there is this class called random access file, which you call get channel. It gives you instance of file channel. There's method map, and that basically gives you a byte buffer, which is the same thing as the mmap. Under the hood, it calls this mmap, and it gives you, the Java NIO byte buffer, and then you can, call this standard byte buffer method, get byte, get long, blah blah blah, to access the file. And do you know what is the disadvantage of byte buffers? The painful point these days. It was not back then in the Java 1.4 times. But do you know what is the pain point now? One of the pain points anyway. Any guess? You cannot have a byte buffer more larger than 2 gigs because it's using addressing by integers. And integers in Java are signed. It means the biggest number you can express is 2 billion, right? 2 gigabytes. Our file has 14 gigs. So we can't use this, or we could, but we could do multiple mappings and then somehow, flip between them. But we are not using that. We will use shiny new thing, which is not even final, not even in Java 22, which was released yesterday. Okay. It is a preview feature which is not meant to be used for production. It's just basically a way how the JDK team can get a feedback on API implementation, performance, and whatnot. And one of the new APIs it's introducing is memory segment, which is like better byte buffer, right? So it removes some of the restrictions, including this 2 gigabytes limit. So nowadays, if you are okay with new features, you can again take the same random access file called get channel and call another overload of the map method, and that gives you map memory segment, and that's what we are going to use. So the idea is that we will map input file into memory. We will have our memory segment, and then we chop the memory segment into chunks, and then we start platform threads. Each will get a chunk, and we'll do this pre-aggregation, right? So if I have, in the case of the competition, I have 8 cores, so I will chop the input file into 8 chunks. We'll start 8 threads. They will do the pre-aggregation, and then I will collect the result. So let's have a look. Let's have a look at this, at the implementation. So maybe one comparison. The reference implementation has what, 50 lines, and half of it are just utility methods, really. So the meat is just this, 20 lines, not even that. But this new optimized parallel IO implementation is already 130, because we cannot use, we are not using, maybe we could, but we are not using all this high level, stream-like abstractions provided by the platform. So what we basically do is, okay, the main, it starts clock, run calculate, will open the file, will check how many cores we have, or the chunk count, because if we have 8 cores, we will have 8 chunks. We create some 2-dimensional array for results. We calculate where each chunk should start. The thing I was talking about finding the end of the line. So basically, it will point finger. Okay, for chunk number X, it should start roughly here, and then it basically seeks until it finds end of the lines, and the next is the start of the new chunk. So this will find offsets at each chunk. We are starting from 1 because the worker thread 0, the first worker thread is starting from offset 0, of course. Need to calculate. So we calculate where the chunk should start, and then here we prepare chunk start, chunk limit, which is basically the limit unless we are the last of us. Unless we are the last, the chunk limit is the beginning of the next chunk, right? So we create 8 threads, and each thread will run this processor. The processor will get its chunk. But important thing I didn't notice is that the new memory segment API can create a slice. So I have my memory segment, again, think of byte buffer, and it can slice it, basically create a view. So so this mapped file is this one big file, 14 gigs. And then per each thread, I will create a view. So each worker thread will include its own instance of memory segment, which will be exactly the part it should process.
I have a question. I might have missed that, but what's the main advantage of using the mmap over the buffered reader? I think
Okay, that's a good question. So the question is, what's the advantage of using these memory mapped files opposed to the buffered reader?
Yep.
One advantage is that the operating systems can cache stuff, can cache the file between executions. Because if you use buffer reader, you can read from arbitrary offsets, and basically when it's mapped, when it's the mapped buffer, everything, and the second execution, everything will be already cached, and it will be really easy for the operating system. And also it's I would say the ability to navigate and treat that as if it was a memory, it makes the processing simpler. You will see this later.
doesn't it also avoid like one memory copy?
Possibly it avoids memory copy. Yes, that's a good point, because it's backed by native memory directly, so it avoids the memory copying. Yes, and it avoids system calls, right? Because there is one system call which is a call to the operating system, normally if I use my mmap, there's basically one system call which says, okay, map me everything, this one big file. But if you use buffer reader, there will be this, oh, read me, read, I don't know, 100 megabytes or something like that, 1 megabytes. And each syscall is expensive, so that's another reason. Okay, so yeah, so the chunk processor will receive its chunk. It will receive this two-dimensional array for results, and it will receive its own index. So each processor has an index, and it's basically then used to set the results to the array. It needs to know its index where it belongs to results. That particular worker. Let's have a look at the meat. This is what we call a hot loop. It's the run method of the worker. And what is it doing? It looks kind of nice, right? Quite small. So it reads, it finds the semicolon and then the end of the line. So it has the position of semicolon, end of the line. Then it will create a name of the city. So basically reads from the cursor up until the semicolon and create a string out of it. The exact implementation is not important, but basically take another slice of the chunk, but only for the limits where we know already the name of the city is starting and ending, then to array and create a string out of it. And then basically do the same with temperature. So temperature is starting 1 byte after the semicolon, and we know it ends where the new one starts. So here we have a string with temperature, we parse the temperature, now we multiply it by 10. The reasons are not that important for now, and basically you can imagine that the temperature is now an integer and is like what's called centigrades. Basically 10 degrees will be represented as 100. 10 degrees, 0.5 will be represented as 105 as an integer. I think it's just not, one reason is that it's nicer to calculate with integer instead of floating points, but that's not the only reason. And once we have the name of the city and we have the temperature, then we have these maps, per worker maps, where the key is name of the city and value are some aggregated statistic per that particular city, for that particular city. And so, okay, if for this city no entry exists in that map, then create a new one and then update it. That's all. And of course, I forgot to run it before starting the explanation. Good news is that this will not run 2 minutes. This should be quite a bit faster, but still slow. So we can have a look. I can cheat and open the frame graph from this version I have prepared at home. We can have a look at the profile. So good news is that the JVM activity is almost gone. There is no GC visible, even if we still allocate, but probably the objects are never promoted and they die young, and basically the G1 is no longer visible. In the second run, there is still some activity, but that's basically just-in-time compiler. And then what else we have? We have parsing double. We have this computed absent into our map. We have this string creation, and we have finding bytes. That's visible here. The running gag. Okay, finished. Great. So now it's 32 seconds. So before it was 2 minutes. Now with this change, the idiomatic Java code 2 minutes. Now this much longer, non-idiomatic, but still quite readable code. It's already how many times? It's 4 times faster. So it's a big jump. And we looking at the profile, this particle, this parse double, it sort of stand out because if you check the code, what is it doing? Is and this string, okay, this string creation, it looks like it's almost completely unnecessary, right? Because we create an instance of string, which means basically here we receive some bytes, and then we need to create a UTF-8, and that string when create, we'll run the validation to make sure that it's valid UTF-8, and we do all of this. We do all of this to create a name, only to use it for a lookup into map, which in most cases will already have that entry, right? Because we have 400 cities, 1 billion rows, so most of the time this name will only return this stats, and that's it. So that's one thing we could eliminate, but it's harder. So maybe we could eliminate this string with temperature, because we parse the string with temperature, and then we create a double out of it, and then we are not using this anymore. Right? So maybe there is a way how we could get this temperature without creating this string, and indeed there is. It is actually not too much code. It's so I have another version which is precisely the same as the previous one, with only one difference: the temperature parsing. I'm no longer creating a string. I just call parseTemperature, which is some handwritten parser. First, it looks scary. Trust me, not. And I have an explanation which hopefully will make it a bit clearer. So I hope this is still readable. Is it readable? If it's not, please give me a shout. You can read it. Perfect. Perfect. So that's the same parser. That's the same parser. And how does it work? You can now ignore that. For now, you can ignore that ASCII table that's basically in the top right corner. So it receives the position of the semicolon, which is just before where the temperature starts. Cities, semicolon, temperature, right? So it sets offset to semicolon +1. It assumes the signature that it's positive, that is negative, so signature is set to 1. It reads a byte from the position where we are now, and it moves that offset. So let's for an example, assume that the temperature is -1.9. So at this point, the byte, if is it -1.9, then in the byte will be basically the number representing the minus, the exact. The way how it works is this comparison. This byte is widened to integer. This is a car. This is also widened to integer, and they are matching because it's the same in ASCII. So okay, so this we are taking this branch. So we change sign from +1 to -1, and we read next byte. The next byte will be the byte will be character 1, which actually in ASCII is 49. So at this point, at this line, this is in B is 49, and from this I subtract character 0. Why? Because 0 in ASCII is 48. So I have 49. I subtract 48. So at this point, at this line, the temperature is 1. It should be, right? Then basically it skips the dot, and then it does the same with 9. So it reads 9. In ASCII, it's 57. It subtracted again 0, which is 48. So the result is 9. It adds it to the original times 10. So at this point, the value in temperature. Oh, sorry, this branch is not taken. So here, what will happen here at this point, basically, the temperature will be 19, and the signature will be -1. So 19 multiplied by -1 is -19, which is the representation we used even before. So the parser it's not super simple, but I think it's quite easy to reason about, and it provides quite a performance boost, because if I run this again now, it should be about 20 seconds. So the one which was creating string and then parsing string to double and then double to integer was 30 seconds. This should be about 20 seconds, hopefully. I'm not using that official instance. I'm using that cheap original shared jittery instance. But yeah, it's about 20 seconds, right? So just changing the way how we parse the temperature, it improved from 30 to 20, which is quite significant boost. And we can check the flame chart graph. Okay, so we have still some, so of course the parsing double is completely gone. We still have some string add because we are still creating string instances like city names. Find byte is starting to be visible, so we should do something about that. But now a little bit of computer science. Because what we want to do is to eliminate creation of that string with the name of the city, because as I said before, most of the time we just use it to do a lookup into that hash map to get a value, and then we are no longer using that string. So we would like to eliminate that. That's quite tricky to do with standard primitives in the Java platform. Put it. I will need this bigger. We could use maybe bytes, but if you use byte array instead of creating string out of it, it's still instantiation. And then byte array and equals is tricky, right? So what most of the people did in the challenge was to craft like their own data structure, and in most of the time it was open addressing map with linear probing. Who has ever heard that? Not many. Okay. Who has ever? This is Faculty of Informatics. Data structure. We should maybe close the doors, otherwise they will not let us in next time. Anyway, most people ended up implementing their own map. We will do that, but before we do that, we do something simple because stupid me. So instead of using a map, we could maybe use an array. We could allocate, if we know that we have 400 cities, or to be compliant with the official rules, 10,000 cities. So we could allocate an array with at least 10,000 slots, and use a very simple algorithm. If I want to insert Brno 42 degrees hot, right? The algorithm could be start from the first element, do a lookup. Is it empty? That slot, yes. Well, insert it there. Okay, good. So now, after first insertion, the array looks like this. Then we have second insertion, 0.5. Same algorithm. Is that start from the first? Start from the first slot, first array of element. Is it empty? No, it's not. Okay, it's not. Then do a comparison between the name of the city in that element and name of the city you want to insert. Is it the same? No, it's not. If is it not, then move to the next element. So we move here to this element of the array. Is it empty? Yes, it is. Then insert it. It's that. So after the second insertion, the array looks like this. And then I do a whole bunch of insertion, easy, and the array starting to fill up. What is the disadvantage of this? Pardon? It's not ordered, but maybe that's not a big problem, because if we had just 400 cities, then I can aggregate all these 1 billion rows, and I will get this 400 entries, and I can order it in the next step. That should be easy, right? Just 400. So that's not the main problem.
It's hard to address it.
Pardon?
It's hard to address it.
It's hard to find. Anytime
if
I'm
you have
inserting.
the name of the city, it's hard to find the right.
Yeah, exactly. Because the time complexity is O n. If I have n cities, in the worst case, I need to do, is it empty? No. And is it matching? No. Okay, next one. Is it empty? No. Is it matching? No. Is it empty? Is it matching? So it's very slow. Next one. Yeah. Pardon? No. This is not a map. This is not a map. This is just motivation and something similar, but simpler, at least simpler to implement. And yeah, the obvious disadvantage is that the time complexity is horrendous. Right?
Sorting would help because we'd be able to use the binary search.
Yeah, but when you are inserting, then you would insert, then sort,
Okay,
then
so
insert and sort.
you would like to use hash.
Yeah, exactly. That's where I'm heading to, right? So the disadvantage is that we are always starting here. We are always starting from the first element, and then we are seeking. So the obvious, or the way how one way to address this with, and this time it is the open addressing map with linear probing for real, is instead of always starting from the start, from the element 0, right? We calculate the starting slot as we hash the name of the city, and for the sake of simplicity, let's assume that the output of hashing function is a number, positive number, basically, a positive number. So it's not negative. I can have such hashing function, and I do modulo and slot count, array size. So the output of this will be some number which I can address here in that array, because if I have 10 entries and whatever the hash is, I do modulo 10 and I will get a number between 0 and 9, easy. So that's where I start, and from now on I do exactly the same thing as before. So I want to insert Brno. Okay, I do this calculation, it will give me a starting slot, it's here, and I do the same algorithm. Is it empty? Yes, I insert it, done. Okay, next one, inserting Prague. Okay, I do the calculation, it will give me another hash, I do modulo, and it will give me another slot. Again, is it empty? Yes, done. Just like that. And there are some problems. First problem is collisions. So my array looks like this. I have Brno, I have Prague, I want to do the Madrid. I calculate hash of the Madrid, I do modulo, and it points to this. But there is already Prague. And I do the exact same thing as I was doing before with array. I do a lookup. Is it empty? No, it's not. Okay. Is the same name, Prague is the same name as Madrid. It's not, then I move to the right. Okay, is it empty? Yes, it is empty. I insert it. So this will be the output if there is a hashing collision. Another problem, wrap over. So imagine I have this initial state. The last slot, the array is not full, right? I have many free slots. The last slot is full. There's Berlin, I want to insert Munich. I do the calculation, and the result of the modulo will be again the last slot. So I do the algorithm. Is it empty? No. Is it matching? No. Hence I should move to the right. But I can't do that, right? That would be array out of bound exception. But I have to do wrap over back where I started. And there is an efficient algorithm for this. I don't need any if else, but in principle it's like that. And I believe the last problem I want to talk about is fill up. Imagine my array is completely full and I want to address parse. So I run the algorithm. Is it empty? No. Is it matching? No. Move on. Is it empty? No. Is it matching? No. Move on. Wrap over. Move on. So it would basically be an infinite loop. So that's one potential issue. And in fact, this is the most extreme case. That the algorithm would never terminate. So whenever I'm implementing this structure, I need to make sure that I will never insert more than I have capacity. I can do some trick with resizing and blah, blah, blah. I don't need to do it here because I know the upper bound. I know that there will never be more than 10,000 cities, so I can just size my array appropriately, so this will never happen. And in fact, if I have 10,000 cities, the array should be quite a bit bigger, because if it's almost full, then it will be very similar to linear probing, right? Because if it's mostly full, I will do, is it empty? No, okay, is it matching? No, and I will need, I will need to do quite a lot of probing until I find the free slot. So this data structure, it likes to have It's called load factor. It likes to have low load factor. It doesn't like to be very loaded, right? So I need to be careful with that. Yeah, that's what could happen. And let's have a look at the implementation. And I will start it. Even this one should be even faster than 20 seconds. So again, we have the code, is growing, but the hot loop is still similar. I still find a semicolon. I still find a new position. I pass temperature with our fancy parser. Then instead of creating a string name, I called find accumulator. Find accumulator. I forgot to show one of the fields in my worker is basically this array of accumulators, right? So accumulator, per each city I will create an accumulator, which is slot in the array I was talking about, and it will have the obvious thing, it will have minimum, maximum, hash for some caching reasons, sum. It will not have a string as its name. It will have a pointer to that original map file, memory map file where the bytes are located. And let's have a look at the map implementation. So I call find accumulator. Exactly the algorithm I was talking about in the PowerPoint, right? So first I do some hash calculation. This is pretty standard hashing algorithm, 17, 31, blah, blah, blah. So this gives me a hash per city. And I calculate that initial position. And this one is basically modulo. So this is if modulo is expensive on CPU. So if I know that my array size is power of 2, then instead of using modulo, I can do this straight. It's the same thing, effectively. So imagine this as a modulo capacity. So this will give me an initial position, and then I do the algorithm. Is it empty? If it yes, then I claim it, right? I create the new accumulator, I insert it to that position. That's my accumulator. I return it. Okay, if it's not empty, then I check the hash. This is just an optimization, you can ignore it. So I check if the name of the entry inserted in that slot is the same as the entry I'm now parsing, right? And if it is, then I return it because that's my entry, or it already exists. And if it's not, then I move to the next slot. Again, this is just some optimized CPU probing to the next slot, including that wrap over. So this will give me the accumulator. And once I have the accumulator, I do this. I do basically the pre-aggregation, and I move cursor to the next position after 1 byte after the new line, and I run this in a loop until I exhaust everything in my chunk. And once I have it, then I take all known empty slots in my array, and I map it to I create the station start instance. This is only happening for this 400 entry, so performance of this is not really that relevant. All this, once I have all this array created, I set it into this global index, global results under index of my work. That's it. And if I check the profile, browser, I can see that this string creation is obviously gone because it's almost not there. It's at the very end after that aggregation with only 400 entries. What stands out? Finding accumulator, finding bytes. Remember, we are finding bytes to find the semicolon position and end of the line. So this is starting to be visible already. And what is this? And this is temperature parsing. Even it's optimized, it still will be optimized more. The performance was 13 milliseconds, 13 seconds. So we started with 2 minutes, and with still kind of basic optimization, we are already on 30 seconds out of 2 minutes. Okay, what else we can do? We have custom hashmap. Okay, now we are getting to more interesting stuff. Modern CPUs are freaking fast. They are freaking fast. You know, don't be confused by the frequency stalling for like 10 years now, about 4 gigahertz, stalling around that. Don't be confused by that. CPUs are
Intel just released the CPU with 6.5 gigahertz.
maybe turbo or something, right? For just 2 seconds.
Yeah.
Okay, so they are super fast unless we make them slow as developers, and we often make them slow. One reason why they are fast, this is Skylake, I think, Skylake CPU, which is 10 years old now, almost. And if you zoom to this part, this is called backend, you can see there is some scheduler and bunch of execution units. If you count, you know, and you can see, you know, there are different types of execution units, and int RU means integer, arithmetical, logical units, and basically, you know, things like summing, right? So, and each core, this is one core, each core has 1, 2, 3, 4 arithmetical logical units for integers. So it means in each cycle, it can do 4 arithmetical operations in each cycle. They are super, super fast. But to be able to do these things, we need to feed it with instruction. It needs to be able to know, okay, if I want to execute multiple instructions in parallel, I'm executing one instruction, and I need to know what will be the next instructions, right? So I can execute it in parallel. One reason what makes this complicated for the CPU are branches, more specifically unpredictable branches. If I have a branch, then if the branch is predictable, it's not that bad, because the CPU has a branch predictor, and if a branch is always taken, the CPU is smart enough to realize it, and then for this execution, and it will speculate that the branch will be always taken, and all these executions units will be happy and busy. But if I have and performance will be good. And if I have a lot of unpredictable branches, then this will suffer, right? Because if it's a branch in 50-50, some, you know, half of the cases it's taken, and in half of the cases it's not taken, then the CPU has a hard time, because it makes a guess and it's wrong in half of the cases, right? And if it speculates badly, then it needs to flush pipeline, blah blah blah, and it makes it slow. And one more thing I will talk about in the next optimization is something called SWAR. Has anyone heard about SWAR? SWAR stands for SIMD within register. So the question is, who has heard about SIMD? Okay, good, pretty good. SIMD means single instruction, multiple data. It's basically, imagine instruction on top of vectors, right? So CPU registers are 64 bits. CPUs are 64, but there are a bunch of specialized vector register with AVX 512. They have 512 bits, and then you can imagine as you populate the 512 bits with stuff, and then you multiply it in one step, and everything, all vector is multiplied at once. That's how SIM works. It needs specialized instruction, specialized register. It's hard to access from Java. Sometimes Java can do auto vectorization, that when it figures out some pattern, it can do it on its own. And there is a incubating API to expose some of the functionality for Java developers to control it explicitly. But it's still incubating, and it's hard to do this in this Java portable way, right? So that's complicated, and that's SIMD. But SWAR is a version of this, except instead of using this vectorized registers, it's using just normal, let's say 64 bits register, but it chops that 64 bits register into, let's say, 8 bits, and then it does some operation inside this 64 register, and the result is basically processing multiple bytes at once. I will show you the example. And I said it's becoming tricky because here I have another iteration of this, and there are a few changes. One of them is I'm no longer using memory segment. Remember, memory segment is our fancy byte buffer, memory save, everything. I eliminated that. One reason is that it has its memory save, it has bound check, making it slow. So what I'm using basically is direct access via unsafe. But that's not the interesting part. The interesting part is this. Let's have a look at the previous version. So in previous version, I have this find byte. How it works? There is a loop, which is, let's say I want to find a semicolon, right? I will find byte, here is semicolon, and it's iterating. And once it finds that semicolon, it returns. So basically, this is super unpredictable branch, because whether this will return or not depends on the size, on the length of the city. Right? So if I have a city with 5 bytes, then it will, or 4, say Brno, then it will check B. Is it semicolon? No. Okay. Branch not taken. Another iteration. R, blah 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 blah. Finally, it will find the end, and then branch is taken. So the predictor will learn. Okay, the branch is most of the time is not taken. So it will assume, it will speculate it's not taken. But then at the end of the day, at the end of parsing, it is taken. So the speculation is wrong. It needs to flush pipeline, and it's slow. And the same will happen here. We find a new position. Again, here will be a lot of bad speculations, and I want to eliminate that. And how I do it is pure magic, because if we look at this, yeah, it's starting to get interesting. Right, we are running out of time. Here is no branch at all. And here, if you check, here is some magic constant. What the hell is that? And now I will not go into details, but you have to trust me that you pass it along, which is 8 bytes, and it gives you a number where, you don't have to trust me, I can show you. I have this block for toys, where I have Brno, semicolon, -33, blah, 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 and I call this semicolon match bits, and let's have a look what happens. So Brno has 4 bytes, and then a semicolon. It gave me some number. It doesn't look cool, but if I view it as a binary, it's more interesting, because let's calculate from right. So here is all zeros. So this is B, this is R, this is N, this is O, and this is semicolon. And at the byte where the semicolon is, the highest bit will be set to 1. So it will give me a number like that, which will basically locate that semicolon within that byte. And then there is another magical function, which is doing, again, some bit manipulation, and output of this will be the length of the Brno, including the semicolon. The name of the length, the length of Brno plus semicolon is 5. And that is here. So basically, this trick will give me this. So that gives me the name, and then I do a little bit of more bit shifting and twiddling, maybe some more masking, and calculate the hash, and then run where it is. Yeah, the final accumulator we know, and you don't need to understand all this bit twiddling, but what you should notice is almost all branches are gone. There's one, right? And that will be in the accumulator, but that will be very predictable. If I run it, it's 5 seconds. 5 seconds from 2 minutes, 5 seconds. And here is time for another tool in our toolbox, which I promised to use, which is perf. Do you know perf? Perf is a Linux tool for watching counters and CPU. CPU is collecting a lot of statistics exactly about things like branches taken, how many instructions you collected, blah, blah, blah. And what I have here is a little script which will use perf. I said, okay, I want to collect these statistics and I want to run my program. So perf log 4. It will run it, so it should be 5 seconds. And it will give me some statistics about that. Okay, so you see that the execution was done again in about 6 seconds. It's jittery. And it processed 120 billion instructions, 13 billion branches, and 600 million misses, branch misses. Doesn't sound too bad until you start realizing, okay, I have 1 billion rows and 600 branch misses. It means on average, I have like every second row has a branch miss. Or it's even worse, like 0.5 would be every second, so it's actually worse. So we need to, somehow figure out, at this point of optimization, typical profiler tools are not very helpful because they will not show you what exactly is going on, because now you are limited by the CPU and it's and how you are slowing it down. So you need to figure out what is causing these misses, and I will show you the reason. Basically, you remember this magical function? I said that it gives you 1 at the byte where the semicolon is. But what if the city is longer than 7 bytes, or 8? Simple. So this one will be 0. So I need to take another 8 bytes, basically move by 8 bytes and run it again. And it turns out that in this testing data set, half of the cities are less than 8 bytes long, and half are more than 8 bytes. It means this branch is still very, very unpredictable. Can I have 10 more minutes? Is it all right? Everyone good? Okay, 10 more minutes. Thank you very much. So I need to eliminate this branch because this branch is fundamentally unpredictable as it is written, and it's slowing me down. So this was version 4. So I have version 5. Yeah, getting there. Version 5, which is even more magical. Because now that one branch is gone, and what I'm doing, instead of reading just one long, first 8 bytes, I am reading 2 longs, so twice 8 bytes unconditionally. Right. So I'm unconditionally that I eliminated branch. I'm always reading, so I'm sometimes doing a little bit of extra work. And then I find the semicolons in one word, in another word, and then there is still a branch, but the branch is taken as long as at least in the first 8 bytes or second 8 bytes there is a semicolon. It means if the semicolon is in first 16 bytes, it means if the city is shorter than 16 bytes, then the branch is taken. And it's almost always, most of the cities in the data set are smaller than 16 bytes. It means this branch is almost always taken. It means from unpredictable branch, we have now predictable branch. So the CPU can speculate successfully. Then it needs a little bit of extra masking to make sure, okay, I read 16 bytes, but the semicolon was at the position 5. It means that the second word, the second 8 bytes, should be completely ignored, but I do not want to have another if. I don't want to have another branch. So again, with a little bit of bit magic, I basically eliminate the effect of that second byte if the semicolon is in the first 8 bytes. And then I do the same. And here is a slow branch. So if there are some cities in the data set which are longer than 16 bytes, so I have a slow branch. So if this unlikely, if you will, branch which is almost never taken and it's a bit slower, but most of the time it's predictable in that whole loop. So let's run it. Okay, it's 3.6 seconds. And without spending more time on this, let's move to the last bit. The last bit is similar. It has 2 or 3 changes. Change number 1 is, I like this especially, it's a hack created by Thomas Wirtinger from the Oracle Labs team, the leader of the Oracle Graal project, and I think the original founder. He realized that, you remember our memory map file, how we mapped the whole file into memory. He realized that, okay, he calculates, he runs the calculation, he exits the JVM, and that operating system has to unmap that file from memory, and it takes lower hundreds of milliseconds, and it's calculated towards that budget. So the trick he came up with was this. Brilliant. Okay, so here's our main method. If there is an argument and it has dash worker, then do the calculation and close blah blah blah. Nobody's calling this with dash worker. Okay, so when you start this, we are not dash worker, so we take this branch, which says start a new process. The same assignment means JVM with all parameters. Pass dash worker. And everything from that sub-process will be transferred to system out. The net effect, it's not important to realize, to understand everything here, but the net effect is that the cost of unmapping is no longer counted towards the execution. The way how this is benchmarked is we print everything, the worker JVM prints everything and exits, and that unmapping part is done in another process, and it's not calculated towards the budget. And that was few totally hacky lines to improve it by few hundreds of milliseconds. It's hell. There are some more optimization. Maybe one more. Can skip this. Yeah, I need to show you this. Sorry, yeah, I cannot not to show. I have to. Sorry, I have to, because you remember our double parser, our number parser, and some of you I could see on your faces. They're like, what the hell? Wait for this. Wait for this. Yes. So this is one of the results of the rules, which is, it's open source, steal from each other. And there was this guy with a GitHub handle Merykitty with single R, who came up with this beauty, because if you remember our parser, even the optimized parser, log 2b, this is our optimized parser, still branch. Is it predictable? Not at all. Sometimes there is minus something because it's negative temperature sometimes. So this is super unpredictable. If you have half temperature, it's negative, half positive, this is not predictable at all. This branch, okay, is there one digit before the decimal point or 2? Again, very unpredictable. So this is again causing troubles for our CPU. There is not a single branch. Nobody can tell how it works. It works. I have to admit that during the competition, I saw it and I was like, yeah, it works, okay, copy it, snitch it, and use it. But I have a colleague, Marco Topolik, with QuestDB, used to work with František, at Hazelpass now he is with us. And he wrote a blog post about this. So if you are interested, it's like basically, it's just, I don't know how many, 10 lines. There are like 5 or 6 different tricks all together. So at this QR code, if you open it, it's QuestDB blog, and everything is explained there. I recommend it. It's a piece of beauty. Yeah, we did this. We can skip this. Yeah, we can skip this.
Don't skip, go back.
Okay, let's have an election. Who is okay to spend more than, I originally promised, which was 10 minutes on this? Hey, raise your hands. Don't be ashamed. If you want to have a beer now, it's all right. Okay, so I'm not skipping. I'm not skipping. Okay, so another, that's not trickery, it's an improvement by Thomas Wirtinger was, do you remember our multi-threaded I/O we did? Where is it? Here, where we said, okay, we chop it, the input file, into segments by how many CPU core we have. So if we have 8 cores, we chop it into 8 chunks. We allocate chunk to a worker, and then worker will do the thing. And then once every single worker is done, then we do the second layer of our second aggregation, and we have the results. Works pretty well until you are in a low 2 to 3 seconds. Then there could be a little bit of irregularity because maybe one CPU core for some reason, because of some noise, is a bit slower than others, right? But it still has to finish its share of work. There is no work stealing, if you will, right? Because imagine František is one CPU core and he is slow because operating system asked him to do something else. Then I have 8 cores in total. One of them is called František, and then 7 cores already finished, but they are all waiting for František to finish, his 125 million lines, right? And if it's slow for some reason, the others cannot help, right? And Thomas Wirtinger came up with this scheme where he says, okay, instead of this, I could chop it into smaller bits, where I do not do chopping up front, but instead of having as many chunks as I have CPU cores, I will say this. I will say, I want each chunk to have 2 megabytes. 2 megabytes, that's all. So I have 14 gigs, total 2 megabytes, that will be a lot of chunks. Then I will have one global atomic counter where each chunk will be able to concurrently claim, a portion of memory to process. So how it works here. So when we are starting, so there is no longer this ceremony with creating this starting and ending offset upfront node. It's totally gone. And here, this is the worker, this is the atomic counter. So each chunk calls get an increment, competing to increment that atomic integer, and gives the counter, basically the number of a chunk. And if the current number is greater than total chunk count I should process, then we know we are done, and that's, we can exit because everything was already processed. But if the number I claimed is less than total chunk count, then I know if that number is 5, then I know that chunk number 5 is mine. So I calculate where the chunk is starting, where is it ending, and then I process the chunk. This was 10 megabytes, and then I do the same. And this is each worker is running this loop and claiming 10 megabytes. Was it 10 megabytes? Yeah, 10 megabytes. So if František is slow, he will process less chunks, but others will help him. Because he will process less chunks, but the others will process 10 megabytes, and basically it evens out the CPU load, and it will eliminate effectively the waiting for one slow action. And there is of course the question of the chunk sizing, because if the chunk is too small, then there will be a lot of contention on this atomic counter, because there will be threads calling this atomic just slow operation too often. There will be CPU coherence traffic, and there will be slow if the chunk size, okay, not 10 megabytes, 2 megabytes. if the chunk size is too large, then the work stealing will not work that effectively. So basically, this is a guesswork to come up with a good chunk size. What else? Yeah, show you that. The one thing I didn't show you, and that's the last coding part, is native image. So you might notice that I'm using GraalVM, but up until now, everything was, the GraalVM has two modes. It can run in just-in-time compilation mode, basically like your standard hotspot JVM. So it's starting in a slow mode, interpreted, different compilation tiers. And that's what we were using up until now. Or it can do ahead of time compilation. It means it take my jar or my classes, translated by, compiled by Java C, and it produce the native image, which is ahead of time compiled native code and executed directly and compiled directly for the CPU. Up until now, we were using this just-in-time mode, and now I have a demo where basically this last block 6 is also, I have pre-compiled it into native code. So now if I execute it, okay, I can get the content because it's no longer starting JVM. You can see it's just calling a native library. So I can do it like this. It's running this ahead of time compiled block 6, and you can see it was done in 3 seconds and something. That is the expected output. And maybe one last thing with perf. If I run it with perf, because I use my own Docker script. No? Yeah, okay, now it's running. We should see, it's there. We should see that almost no, well, 70 million branch misses. Well, 70 million branch misses for 1 billion row, it's not too bad, right? It's just less than every 10th row had on average had a branch miss. Sorry, not notification miss, branch miss. So not too bad. And another metric which I like is instruction per cycle, because that's showing how many instructions in each cycle it's able the CPU to process, which usually correlate, not always, but usually correlates with this branch misses. Because if I do not have misses, then I can make all these execution limits in CPU. I was showing you before that picture busy. And here it says that on average during the execution, in each cycle, the CPU could process 1.38 instructions. I would say not great, not terrible. Okay, we are done. We are there. Observations. Unsafe. There has been a war on unsafe in the Java world since, I don't know, 2015 or something. You know, Oracle at some point announced that it will no longer be available for developers, and then they realized, oh, okay, there are so many libraries, frameworks relying on that, and back then there was a lot of drama. Now we are slowly getting replacements, such as the memory segment API I was showing you. It's not there yet, because if you check the leaderboard, all top solutions, they rely on unsafe, all of them. So yeah. Another observation, GraalVM, again, this is the scoreboard. There's only one in the top solutions, one solution, number 4, which does not use GraalVM and native compilation and use OpenJDK, done by Serkan Özel, former Hidrokas developer. But everyone else in this top was relying on ahead of time compilation. Another observation, no vector API, that's the incubating API for accessing the same instructions I was talking about. The reason is, for one, it's still incubating, and because it's incubating, the GraalVM it supports it, but it's not very fast, right? So basically the trade-off was either I use GraalVM native, it means I have fast startup native code, but slow vector, so slow I can't use it, or I use hotspot, I can use optimized vector API. I can use all these nice SIMD instructions, which I could not use, but I have a slow start. And this one solution based on the hotspot was heavily relying on the vector API. So that's actually a good thing because it's showing that it's becoming usable. You know, without there is no way that without this SIMD instruction, Serkan would end up on the fourth place. So that's promising. Last thing, cheating. Some people try to cheat. One way to cheat is if you know the name of the cities up front, you can construct a special hashing function which will never have any collision. And if you never have any collision, you don't have to handle collision. It simplifies the hashmap implementation, because if you don't have any collision, you don't need to do this. You know, you remember the algorithm? If slot is not empty, you need to compare the names if they are the same. But if you know that there are no collisions, then if the slot is not empty, then it must be your city, and you don't need to check that slow name check. But that's illegal. That's cheating. One of the rules was it has to work for any input within that, you know, and it's and basically the Gunnar said, no, you can't do that. Your hash map has to handle collision. Yeah, another way people try to cheat, usually unintentionally, was abusing the dataset, right? So map implementation, which could accommodate for this 400 keys from testing dataset, but would fail or end up in infinite loop with 10,000 dataset. What I haven't covered in this talk, Hyperfine. Hyperfine is awesome tool. I haven't covered it, but I'll show it anyway. Sorry, Martin, because it's so awesome. Hyperfine is a little tool for quick benchmark. Hyperfine. What the? Okay, it basically executes whatever you want multiple times. It do some warm-up iterations, and then will show you some basic statistics. It has some parameters. I didn't know it before this competition, and it's perfect to get some quick feeling how is your implementation performing. So that's good to know. Hyperfine. I was not talking about hashing functions at all. They were super important because they are very slow and very fast hashing functions. So I didn't cover this at all. I didn't talk about instruction level parallelism. Maybe that's something for next time. And register splitting is really a juicy topic, maybe for next time. And one thing, this competition started at 1st of January, ended on the last of January, and about in the middle of January, I wrote my first implementation, and then Marko Topolnik benchmarked it, and he was excited. You are pretty good. Checking Thomas, and yeah, Thomas was ahead of my initial implementation. And back in the middle of January, I was like, yeah, I don't mind. Thomas is a genius, and I don't mind if I lose to him. Guess what? By the end of January, I lost to Thomas. So that was a good prediction. And boasting time. So I was third in the main competition, but there was like side competition, which was not restricted to 32 cores. So to 8 cores. It was using the full cores from all CPU, and somehow I don't know how I managed to win it. I was not optimizing for this at all, but I call it accidentally scalable, my implementation. But you check the deltas, right? It's 323, 326, so 3 milliseconds deltas. But Gunnar told me that he ran it multiple times and the results were consistent, so I consider myself to be a winner. Oh. Was it useful?
Yes.
It was fun. No, I mean the competition. This talk was not useful. I don't need to ask. I was asking myself rhetorical question if that was useful. I think it was. For one, the Hyperfine. For second, I show you a little bit of perf, but I use it more, and I learn to identify some deeper things inside the CPU thanks to perf. So that was good. I made some friends while competing this. It's a vanity metric, but it gave me, like, I don't know, 700 Twitter followers because of this. So that was good too. I can use it to promote QuestDB now. And yeah, it was fun. It's fun. I can recommend it. I did it. If you happen to know the Advent of Code, which is every December, I did that. This is way more fun for me anyway. So thank you very much for this. If you like to talk, then you should know big part of it was based on a blog post again by Marko Topolník. So if you go to this URL and then you can read about this at your own pace, at home, relaxed, because almost everything is there as well. And that's all. That's all. So Martin, only 90 minutes, not too bad. So thank you very much for your attention. Thank you for bearing with me. And I presume, Martin.
You know, I would prefer to take questions now, so
All right.
that's recording.
Okay. So if there are any questions, yeah, there's one question.
Yep. So from block 4 solution, you start to rely on semicolon search method based on map, right?
Yes.
And you assume that it's only like ASCII semicolon, right? 1 byte. But city name may be UTF-8.
City name may be UTF-8, that's true. But yeah.
Is there a possibility that UTF-8 will have like multi-byte character that will contain semicolon as byte?
No, okay, the question is, okay, I'm searching for semicolon by bytes, but the input has to be arbitrary UTF-8 encoded string. Can this cause any problems? The answer is no, because the UTF-8 for ASCII is the same as ASCII, right? So the top bit, if the top bit is 0, it means it's ASCII. It's between 0 and 127. Then the ASCII encoding and UTF-8 is exactly the same. The problem is with UTF-8 multi-byte characters, right? But if it's UTF-8 multi-byte characters, then the first bit is not 0, it's 1, right? So it's not, basically. It's big because the way how UTF-8 is designed, this cannot happen. This cannot happen. If you have UTF-8 encoded string and you search byte by byte for ASCII string, you know, it will not cause any bug. Any other question? Yeah?
In that super multi-small chunk solution, and we are splitting the file by the megabytes, there was still some searching for the end of the
Yeah, sure. It has to be. There was a little bit. Where is it? Yeah, here. Okay, so I claim my chunk, and if the chunk is not 0, it means it's not the very first chunk. Then it's still seeking until it finds the end of the line, because again, I cannot start to search in the middle of a line, right? So there is this byte by byte searching or seeking, but this is only happening once per chunk. So if my chunk size is 2 megabytes, then each 2 megabytes process, the worker will do a little bit of this unpredictable branching, but that's rare, right? Because if you think about it, 2 megabytes, if on average the line has 10 bytes, then it's many hundreds, thousands of lines per one unpredictable branch. So that's not bad. That's not too bad. But yeah, this could be optimized further. I think some people also use this SWAR technique for this. This is simple. This code, by the way, is not my code, which I use for the competition. That's again written by Marko. The reason is that my code is not really suitable for any explanation. I have it here. It's like when cat is running on your keyboard, and there's a lot of duplication. It has its reasons, but it's even more like less comprehensible than the one I was showing you. That's the reason. Marko basically, after the competition, Marko prepared this step-by-step improvements, and he was focused on readability. unlike this craziness. Yeah, Martin?
What this craziness do?
Okay. Well, I thought that you were the one, hiring. Okay, the reason why it looks like everything is duplicated is to exploit this instruction level parallelism. Because imagine, even if I have zero unpredictable branches, then the way how it still works is find the semicolon, and only after you know where the semicolon is, you can parse the temperature. It means you cannot parse temperature. The CPU cannot really cannot use much of a parallelism because it cannot parse the temperature until it knows where the temperature is. So my realization was, okay, so what if each thread is processing two independent chunks in parallel? Because the optimized block 6 solution I was showing you, that was each thread claimed one chunk and was sequentially processing one line by one in that chunk. This, my solution, is each thread claims two threads per, two threads at the same time, and then it's running everything twice. And the reason is that then it can keep that execution limit busy, because that's the instruction level parallelism. You have more stuff, more independent stuff to calculate, right? Because here you are calculating some mask for one long. Here you are calculating the same mask, but they are totally independent. So if the CPU has enough execution units for calculating for some bit operations and blah blah blah, then the scheduler inside the CPU can run this in parallel, and that's one reason why the code looks so horrible and it's so long. Yeah, it has almost 700 lines, and I didn't really want to torture you with this.
So basically, if you run your code right now on the perf, you basically have the better number when it comes to the instructions per cycle, right?
Yes.
So you should have much higher number in here because of this hex that you did.
Yeah. So I can try to run this. The first execution will be likely slow. Okay, it's using the Guardian native, and yeah, the execution was 2.7, and that before was 3.2, so it's a bit faster. And if I run this with perf, I don't remember the syntax, so let's do this. I run my code with perf, then the instruction per clock should be higher indeed, hopefully. So instruction per clock per cycle 2.65, and in the educational implementation it was 2.38. So yeah, our experiment is consistent with your theory. Any other question? Right?
How much time did you spend playing with this?
Evenings.
How many
Many.
evenings?
All of them.
Many evenings. No, the truth is that I joined in the middle, right? So it started on 1st of January. I joined around, I don't know, 15, 16, that screenshot from WhatsApp I was showing you, it was from 17th of January, and it was one of my first implementation, and actually my first implementation was using this instruction level parallelism, this copy. You can cut, right, from the video recording. And here it's actually copied only twice, but my original implementation, everything here was 4 times. I think I can find it in history, maybe. Initial submission. Yeah, have a look at this beauty. Cursor. Yeah. Yeah, that's L, that's not it. Yeah, here, see? A, B, C, D, and it's even more complicated because at some point I was trying to maximize the utilization of execution limit. So I was playing with ordering of independent instruction. Basically, my attempt was if something is expected to have high, let's say, memory latency because it's random memory access, then I want to have it as early as possible, and then have a bunch of independent instructions which can be executed while that loading from memory is still being blah blah blah. So this was 4 times, and then I realized, okay, that was suboptimal. It was too much because of the original implementation, the application by 4 was optimal. That was the fastest one. But then as I was adding more and more code, it was not, because of the phenomena called register spilling. And I think if I go to register spilling, Martin will kill me.
No, I will not, but let's continue this overview.
Okay, so once more, thank you very much. And I understood that we do have a beer, which is a good news. So thank you very much, and let's stop there.
So just to finish, room A321, there is food, there is beer. Also keep the pens, that is for you. And I just want to add on top of what he was saying, this is not only fun, this actually resulted into several JDK improvements and also GraalVM improvements, which you didn't mention. So
I'm the guy for fun, not for work. That's what my boss says.
I think